Okay. Well, I mean, I know that a lot of what we've done so far has been at a fairly basic level, and some of it was review. But we're going to start to get more into the meat of the course now. So today and tomorrow, what I'm going to do is talk about different ways of actually building a quantum computer, which obviously is an important task. It's not something that I'm really an expert in, but I can give you at least kind of the general idea of how these things are done. A lot of the kind of the early design of quantum computers and the filtering to try to figure out which systems are good candidates for quantum computers makes use of something that's known as the DiVincenzo criteria. Try here. And so the DiVincenzo criteria are conditions and properties that a system has to have and capabilities that you need to have in order to build a small quantum computer. To build a big quantum computer, you're probably going to need some additional properties. In particular, you need some properties that are necessary for fault tolerance. And actually, these criteria are not absolute. You definitely must have them. There's certain systems and certain situations where you can say, oh, well, we can relax this criterion. We can get away without it altogether in some cases. But that makes things harder. And kind of the standard picture of what a quantum computer can do does satisfy these criteria. And certainly, it's a good starting place to look at when saying, I want to build a quantum computer. So what are they? So there's kind of 5 original ones that tell you about building a quantum computer, and then 2 more that David DiVincenzo added a little later that are useful for quantum communications. So first, we want a scalable physical system with well-characterized qubits. So in other words, we need something that can serve as our storage, our computation space, our memory in our quantum computer that's going to be broken up into qubits. Although, of course, obviously, having specifically 2 states in each subsystem is not important. It could be qcrits with 3 states or qdits with d states. But qubits is certainly the most common thing. Well-characterized means that we should know the basic properties of these qubits so that we can, for instance, control them and manipulate them as we like. So for instance, you usually need to know the energy difference between the ground state and excited state. And you want that. It doesn't necessarily have to be the same for each qubit, but you certainly want to know them for all the qubits, because you need to know that in order to excite from ground to excited. You need to know the relative phase difference that you accumulate over time, things like that. And scalable is important as well, because it's not enough just to have 1 qubit. You want to be able to build 2, 3, 4, 5, 20, 50 qubits, right? And of course, as it gets bigger and bigger, that can potentially be a bigger and bigger challenge. So then the second condition is the ability to initialize the state of the qubits to a simple fiducial state. Such as all zeros. OK, so at the start of the computation, we need to put the qubits in a standard state. And usually, you want it to be a pure state and even a tensor product state. Although, again, like I said, these conditions are not the be-all and end-all, and you can sometimes get away with other things. But certainly, the standard thing to say is the qubits in the system start off in the state 0, 0, 0, 0. So you need long relevant decoherence times. Much longer than the gate operation time. This is, I mean, obviously, if the qubits decohere very rapidly, they go from superpositions to mixed states. The environment is measuring whether you have a ground or excited, you have 0 or 1. That's not going to be a quantum computer. That's going to be a classical computer, right? And the relevant length scale for this to happen is the time it takes to do your quantum gates, right? So if your quantum gates are very slow, then your qubits need to remain coherent and also not get flipped or whatever for a very long time, because you need to be able to do many gates before whatever that time scale of errors kicks in. Whereas if your gates are very, very fast, then you can make do with much shorter decoherence times, because, again, if that's the case, it may be still true that you can do many gates before that time kicks in. OK? Does that make sense? So it's kind of the gate operation time. And obviously, different kinds of gates can take different amounts of time. For instance, often it's the case that a 1-qubit gate is fast and a 2-qubit gate would be slow. And in this case, usually we're talking about the slower time. And so that kind of sets the time scale of everything that you want to work in the system. We need a universal set of gates. And hopefully you remember what that is. Yeah?
Can you specify what exactly coherence means?
Yeah, so from the point of view of these criteria, all I mean is that well, OK. So when it's phrased this way, what it's actually talking about usually is the T1 and T2 times. So if you have a system, a lot of systems experience the same kinds of decoherence mechanisms. And so one of them is dephasing. So if you write that as a completely positive map, one way to think about it is with some probability, there's a phase flip. OK? And I guess in this case, it would be probability per unit time. And so then it's the question of what's the time scale for that. And so that's a T2 process. And the other thing that's very common is a T1 process, which is an amplitude damping process. So you have a ground and excited state. And the excited state will sometimes emit a photon, say, and collapse that back down to the ground state. And so what's the time scale for that to happen? And since we're talking about time scales, it's not, these are, you can say, well, what's 1 over E probability of ending up in the ground state, something like that. But the exact time is not that relevant, because in any given qubit, it might be, you might get the error sooner or you might get it later. Now, there's lots of other decoherence mechanisms that you can have. Decoherence in that context then becomes a proxy for just kind of any kind of error. And this is one thing that's missing from these criteria, is that actually you want, not, or at least not explicitly stated, you want your, and in real quantum computers, your ability to control the qubits is not perfect either. And you want kind of the number of gates that you can do before, on average, you get an error to be fairly large. And that's kind of an expansion of this criterion to something that's closer to what you actually need to have. Is that a good enough answer?
Yeah.
OK.
Why exactly does decoherence happen so prevalently?
Yeah. OK. So there's there's a couple of different reasons, I would say. So, so if you have any kind of interaction, and they're different, but kind of also the same in some sense. So it's not going to be able to say exactly why it happens. But anyway, so if you have, this is a qubit over here, OK? It has a 0 and a 1 state. And we have here some other atom that's nearby, or some other quantum system. And it has some interaction with this atom, right? And maybe that interaction is a bit different from between the 0 state and the 1 state. And so that means that if this thing is in a superposition, and this thing is interacting with it, then after a little while, this qubit will become entangled with this qubit, right? We'll get something that we could call a 0, 0, alpha 0 plus beta 1 will become alpha 0, 0 plus beta 1, 1, right? And then when you trace over this qubit, this will be just a mixture of 0 and 1. And that's kind of the complete dephasing. Now, in reality, this won't become completely entangled. It'll just be partially entangled after some given amount of time. And that's the partial dephasing when you trace over the system. So the point is that whenever the environment is learning something about the state of your system, that's dephasing in whatever basis it's learning. So another thing that's relevant is, suppose your 0 and your 1 don't have exactly the same energy, which is common but not always the case. So the kind of the natural Hamiltonian of the system then is, we'll write down examples very soon, but is going to give you a phase rotation of the 1 relative to the 0, right? The thing is that so long as that energy is kind of completely known and completely stable, that's a phase rotation that you can kind of cancel out by keeping track of it or some other technique. But if it changes a little bit, or if you don't know it quite right, for instance, if there's a magnetic field that causes a little bit of an energy shift, then the amount of relative phase change between 0 and 1 is different from the amount that you're expecting. And you can think of that as a phase error, right? There's a little bit of phase error in that system. And so it's, again, the same sort of process. So those are kind of probably the two main causes of dephasing, and they're both very common.
Thank you.
OK, so universal set of gates. So we talked about what universal sets of gates are. And obviously, if you want to be able to do an arbitrary control on your system, you need a universal set of gates. That's kind of the whole point of that. And then here's the fifth one, a qubit-specific measurement capability. So in other words, at the end of the computation, we have to be able to measure our qubits to get some information out. And we would like that to be something that we can look at a specific qubit and measure it and see what its value is. We don't really want, although, again, you can sometimes get by with saying, well, we know the average value of measuring all the qubits in the system. That would be inconvenient. We'd have to kind of somehow arrange our computation so that the average was telling us the outcome rather than just some specific qubit that we're looking at. OK? So this kind of breaks down into stuff that we've already discussed, right? A circuit consists of state preparation. It consists, that's this condition. Well, the circuit, first of all, it consists of qubits that are making up our computer. And then we should be able to prepare states. We should be able to do gates. And we should be able to do measurements. And we want to do all of this without having so many errors that the outcome is unrelated to the circuit we really wanted to do. OK?
So the qubit-specific measurements, could you have like on a single qubit? But
yeah, so it's most convenient if you can kind of selectively say, I want to measure the third qubit in my computer and not the other ones. That's helpful for a bunch of reasons.
What if it's entangled with another qubit in the system?
Oh, yeah, that's fine. The point is that what happens then is governed by the rules of quantum mechanics, which is you measure this qubit, you get some outcome, you project the whole state on the portion of the state that corresponds to that outcome. That's just what quantum mechanics expects you to do, and certainly what, if you're writing an algorithm, you should expect to happen when you do a measurement. Any other questions? OK. So then I said there's two more conditions. So these are the ones for computation. And so there's two more that apply for communications. If you want to interact your quantum computer with another quantum computer that's far away, or if you're not even interested in that, but you want to build some kind of communications device, like, for instance, to do the superdense coding that we talked about. What kinds of conditions do you need? And so for this, he invented some additional terminology. There's flying qubits and stationary qubits. So stationary qubits are ones in the computer. And they stay there, and you can do quantum gates on them. Flying qubits are ones that move easily. And it may be hard to do computation between different flying qubits. And the typical flying qubit is a photon, right? Because that's something that certainly moves very easily, and we have a lot of techniques for getting it from one place to another. It's hard not to get it from one place to another. OK, and so then the other two conditions are the ability to interconvert between stationary and flying qubits. And so that's useful if you really don't have the ability to do computations between the flying qubits. You can then do things, any computation you want to do, you do with the stationary qubits, and you convert to the flying qubits to send them somewhere else. And then, of course, you want those flying qubits to actually get there. So that's the last condition. The ability to faithfully transmit flying qubits between specified locations. And so this means that you send your flying qubit, and it gets to where you wanted it to go without significant error. OK? And so people have, since David came up with these criteria in the late 90s, I think, people have made lots and lots of progress in building quantum computers. And we can do much, much better and have a number of different systems that can satisfy all these criteria. People have not done so well in kind of this particular condition. Certainly, photons, we can easily transmit them between different locations. But converting back and forth between photons and the other stuff, we do have ways of doing that. But the progress has been much, much slower. So the main activity and progress that we've seen over the past few decades has been to actually build the quantum computers. And quantum communications, while it looks easier in principle, has somehow not proceeded as quickly. So what I'm going to talk about today and tomorrow are two of the main techniques that people are using to build quantum computers today. These are the leading techniques. And then if I have time, I'll maybe say a few words about some other things. So those two, well, OK, before I do that, let me make sure there's no, see if there's questions on the DiVincenzo criteria. OK, so you'll get to see how these work with, oh, this is broken again? Yep. Nope. OK. Well, oh, wait. There we go. OK, so that will be up there for months, I think. So the two implementations that I wanted to go into some detail about are ion trap quantum computers and superconducting quantum computers. So today we're going to talk about ion traps. So the idea in ion traps is that our qubits are going to be individual atoms. And usually, people pick a group 2 atom. So if you look in the periodic table, that's the second column. And what's special about group 2 atoms? Well, their outer shell has 2 electrons in it, right? And so but these are ion traps. So what we're going to do is we're going to take away one of those electrons. So the ions will have a charge +1. And then there's 1 electron in the outer shell. And that electron is going to be our qubit, whether it's in one of 2 possible states. So we're talking about things like beryllium, I think, is an example. Right, OK. And because this thing is charged, that means it'll interact with electric and magnetic fields. And so there are designs for kind of magnetic bottles that will hold such a thing in place. And that's the ion trap. And so the advantage of this type of system is that a single atom is always a single atom, right? It has certain properties, and you know what those properties are because you can study that particular atom and study its spectroscopy. You know what the energy levels are. You know what the angular momentum of each of those levels is, and so on and so forth. And so that's a very good candidate for point 1, right? We have very well characterized qubits. And the other thing is that because we're holding these ions in a magnetic bottle in a vacuum, there's not much else around. Okay? And that's going to make them pretty well isolated. And yet we can control them by manipulating the electric and magnetic fields by shining lasers on them. And so that's going to be a very good candidate for condition 3, right, where the decoherence times are very long. So let's see. So we have many energy levels, and of course some of them will be very unstable, right? You put it in that energy level, and it'll very quickly emit a photon and relax to some lower energy state. But again, we can study the spectroscopy of this atom and find 2 states that are both quite stable, and those will be our ground and excited states, our 0 and 1. So we're going to call ground to be 0 and excited to be 1. And so the first thing to do is to figure out how to do single qubit gates on this. So the Hamiltonian of this system is going to be the atom Hamiltonian, plus we're going to shine a laser on it, and so we'll have the laser Hamiltonian. Now I'm not going to give the full Hamiltonian of either of these things, just kind of approximate the parts of it that we need to study this. And so H atom, well, we're only going to focus on these 2 states. And we might as well assume that this ground state has 0 energy. So H atom is then just going to be E times the excited state, projector on the excited state. OK? And H laser, well, H laser is basically this, at least in the approximation that we're working in. And omega is E over H bar is the frequency of the laser. And so the laser here, you see, has the frequency that's equal to the energy difference between the ground and excited state. So it's what's called on resonance, right? And that means that when you shine this laser on this atom, it will cause the atom to transition from the ground state to the excited state or back. And so that's what this Hamiltonian is doing, right? It's saying excited state goes to ground state, and ground state goes to excited state. And this e to the I omega t is kind of making up the energy difference between the ground and excited state. And that energy difference is being made up by the energy of the laser, of course. And that causes a relative phase shift. OK? And then this J here represents the strength of the laser. So if we have a very faint laser, J will be small. If it's a very strong laser, it'll be large. And that will cause this transition to happen faster. OK, so suppose we have this. And the point is that J is something that we control. E is given to us in this system, although we've selected the ground and excited state, so we have a little bit of control over big E. But J is totally in our control. We can turn the laser on. We can turn it off. So that lets us do some sort of control on this atom, right? If we don't want it to do anything, we just turn J off. And actually, it still is actually doing something. I'll get to that in a minute. And then we want it to do something. We want it to transition between ground and excited. We'll turn the laser on and increase J. And so what will that do? Well, if we started with the ground state and we turn the laser on, then over time we get this state. Right? So you have a cosine and a sine. So this is just simple differential equation solving. At time 0, we have just the ground state. As time passes, we get more and more excited state until we have all excited state. And then it starts to go back to the ground state. And so if you look at this, so what's the probability of ground at time t? Well, it starts out at 1. And then it goes down to 0. And then it goes back up to 1. And then back down to 0. And then back up to 1, and so on. OK? So that's what should happen if this were actually the exact Hamiltonian. But of course, in reality, things are not perfect. And so this is the ideal case. And in the real system, there's going to be some decoherence. So what does decoherence mean in this case? Well, we have a superposition of ground and excited, but sometimes there's a phase shift, right? And so what's that doing is that's sometimes collapsing the superposition. That's one way of thinking of it. So kind of at every time, we can imagine a small probability that the superposition collapses. And instead of ground plus excited, we have a mixture of ground and excited. And that will kind of mix things up here, right? So if we happen to be just at one of these ends here, and it collapses and nothing happens. But if we're somewhere in the middle, and it collapses, then we'll go back down here, effectively. And so what we're doing is we're adding this thing with something that's shifted by some amount, which is a random amount, because this could happen at any time. And suppose, in fact, it happens right in the middle here. So it's a 50-50 chance of ground and excited. Well, then we're mixing this with the opposite thing. And you'll just get a flat line from then on. So, so what actually happens then in the real system is that you might start at 1 or very close to 1 and then go down here. But you won't get quite to 0, and you won't quite get back up to 1 either. And over time, the oscillations will get smaller and smaller. Now, this particular thing that I've drawn is actually a pretty bad qubit, because you see after 1, 2, 3, 4 gate times, you've already lost kind of most of your coherence. So that's not a very good way to satisfy that high decoherence time. Now, the ion trap is very, very clean. So you can do thousands or tens of thousands, maybe even more, actually, oscillations like this before you start to see an appreciable loss of coherence. And so this is kind of the very basic measurement that people first do, usually, when they try to build a qubit, is they measure, they do this Rabi oscillation. And measure the T2 time, the time to the kind of the decay rate of the envelope of this sine wave. OK? OK. So the other thing about this is that this is a good way to do single qubit gates, right? Because you can say, well, I started in the ground state, the excited state, maybe some superposition. And if I turn on the laser for just the right time, I'll go from the ground to excited. So that's a bit flip. Because in that same time, I can go from excited to ground. And if I go from superposition, I'll go to the corresponding superposition. But I can also do it for half a cycle, right? And instead of, well, I guess half a cycle is ground to excited. So a quarter of a cycle. And so then I'll go from ground to ground plus excited. And that's kind of like the Hadamard. I think it differs maybe by a phase shift, but that's not too important. OK? So this is one way to do single qubit gates. But this is just single qubit gates around one axis of the Bloch sphere. Do you guys know what the Bloch sphere is? OK. Single qubit gates around one axis of the Bloch sphere, right? It takes superpositions. It takes basis states to superpositions, or some combination thereof. But we also need, remember, in our universal set of gates, we had a phase rotation, which is the z-axis of the Bloch sphere. So how do we do that? Let me see what's right here. No. So this is, let's see. So we have single qubit x rotations by turning on laser. And single qubit z rotations. Well, so what do we want to do for a z rotation? We want to change the phase of 1 relative to 0. So how do we do that? And the answer is, don't do anything. Why? Because what happens if we don't do anything? Well, this laser is off, so the whole Hamiltonian is here. And so what evolution does that do? That means that the 0, the ground state, goes to itself, and the excited state goes to e to the minus I omega. It's the same omega. This I e t over h bar. Right? So it's getting a phase shift of the excited state relative to the ground state. So really, if we're if we're not doing anything, the z phase rotation is happening all the time. Now, of course, if you don't want to do a z phase shift, you need to take that into account. And the best way to do that is just to kind of, the timescales in the ion trap tend not to be so very long, so very short. So you can kind of keep track of time, and you'll know how much time has passed. And so you'll know what the relative phase shift between ground and excited ought to be. And then if you want to change that, you can just kind of adjust your notion of what the time is. Now, that's fine when there's a single qubit. It's actually a bit more complicated than that when you have multiple qubits. Then you have to actively do something to make one of the qubits get a phase shift at a different rate than the other ones. Let's see. Yeah. And so the way to do that is usually, again, going to involve lasers. And you have a laser that has a different phase on that particular qubit. OK. And then once we have these two, that's enough to get arbitrary single qubit gates. So I should say this is not the approximate universality case, because the approximate universality case would be if we have some very specific thing where we can only turn the laser on for pi/2 time here, right? And then we would get the Hadamard-like thing where we get the ground state to ground plus excited. But we can turn it on for an arbitrary amount of time. That's straightforward. And so we can get rotation by any angle, any amount about the x-axis. And by adjusting our phases, we can get rotations by any amount that we like about the z-axis. Okay? And if you can do x-axis and z-axis rotations, then using Euler angles, you can get any rotation. So this gives us a universal set of single qubit gates. OK, so there are questions on this.
I didn't understand why by waiting I will get a phase and I'll get a z rotation. Can you please explain?
Sorry, so waiting, you don't understand why you don't get one or why you do get one?
Why do I get one?
Why do you get one? Yeah, so the Hamiltonian in that case, this j is equal to 0. Yeah. We've turned off the laser. So the Hamiltonian is just this. And so what does that do? The ground state goes to the ground state. The excited state goes to the e to the minus it e over h bar. OK? So that's a relative phase shift of excited versus ground, that's the z rotation. Yeah?
You said that we kind of need more sophisticated techniques if there's multiple qubits, because if we just wait, then everything rotates the same.
Yeah.
So can you still have exact rotations however you want for each individual qubit, or does it become
Yeah, no. In principle, you can, and it's not even that difficult. So, but the way it works is a little bit subtle. Okay, so so I said what you have to do in order to just take the single qubit, when there's only one qubit case. So I said you should keep track of time, and so you have some clock that you're comparing to. And if you want to do a phase shift, then you just don't update the clock for that time. So in reality, what's the clock? Well, the clock is actually, because sometimes you're going to do these x rotations. And so the clock is the phase of this laser, which has the same frequency, and it's oscillating at the same rate. And really what you want, and this e to the I omega t is going to come in there, right? So if you wait some time and then you shine the laser on it, then that's the t that happens here, right? Which is what time did you turn it on? And so if you really want to do a phase shift, what you have to do is you have to adjust the phase of the laser relative to the thing that's happening in the atom. Otherwise, that phase shift that you thought you were accumulating is going to vanish when you do this gate, this x rotation gate. Okay, and so if you have a separate laser for each atom, what you want to do is you want to adjust the phase of one of those lasers and not the other ones. Okay, and you can do that using kind of standard optical elements, slowing it down or bouncing it, through some some longer path length. That's usually the general way to do it, right? And then the path length is going to determine how long it takes, and that sets the phase. So that's the real way to do it. Any other questions? OK. So the next step, so the 2-qubit gates are considerably more complicated, so I'm going to leave those to later. So the next step is measurement and state preparation. Let's do those. So the usual way they do this in the ion trap is to cheat. I mean, it's not really cheating. If it works, it works. But in particular, what we're going to do is we're going to go outside of this qubit space and then bring in an additional state. So we have now 3 states. We have, let me put this one up here. Oh, sorry, that's probably not visible. OK. So this is the ground state. This is excited state. And let's call this state up here F. OK? And I picked G and E to be very stable. So if we put an electron in there, it's going to stay there for a long time. But F, we're going to pick to be very unstable. And so if we get something that's in F, it will very rapidly emit a photon and go back down to G. And the reason we want to do that is then if we shine a laser that's at this frequency between G and F, what happens? Well, if we shine it relatively strongly, then the atom will very quickly absorb a photon. It'll go from G up to F. But then F is unstable, so it'll emit a photon again and get back to G. But the laser is still shining on it, so it'll absorb another photon and emit another photon and absorb another photon and emit another photon. And the thing is, we can have a photodetector set up to see these photons. Right? And there's a lot of them, so it's an easy thing to do. You don't need a super sensitive detector. Whereas, what happens if the state is in E? Well, if it's in E, the laser is not on resonance. So E doesn't get excited up to F. Now, you have to be careful when you pick F that there's not some other state that's above F that's that same energy difference above F, right? Otherwise, you would get some excitation. But if you picked your levels carefully, there's no such level, and E just stays as E. And so what you're doing is you're seeing light if there's a G, and you're not seeing light if there's E. So let's see. So this is called the cycling transition. So that's a pretty good way of realizing this 0.5 with qubit-specific measurement capability. The measurements that you get this way are very reliable, have very low error rates. OK? And if you look at this level diagram, you can see that it's also very easy to prepare your states in the ground state this way, right? Because suppose you happen to be in the state E to start with, but then you shine a laser that's at this EF transition. Oh, I can use another color. Suppose you do that. I don't know if you can see that difference. But anyway, suppose you shine on this EF transition, well, the atom will quickly absorb a photon, but then it'll emit a photon and go back down to G. If we start at G, we'll stay at G, because we don't have this laser on. If we start at E, we'll also end up at G. So either way, we're kind of resetting it to end up at G. And so that's kind of the condition 2 of preparing the initial 0 state. Now, I should say this is really specific for a single atom. When we get to 2-qubit gates, you'll see that there's another element of the preparation that's actually much more difficult to achieve. But I can talk about that then, too, a little bit. OK? So are there questions on this? OK. So then let's move on to those 2-qubit gates. OK, so what we're going to do now is we're going to imagine we have this trap with 2 atoms in it. And you can do the same thing with 3, 4, 5, 10, 20 atoms. Eventually, it becomes hard. You have many, many atoms in a trap. If I have time, I'll talk about it today. Otherwise, I'll say a little bit tomorrow. But for the moment, let's just think about 2. OK? And both of these atoms have charge +1, remember. So they don't want to get too close to each other. They tend to repel each other. And we're going to think about a linear trap. So they're confined in this direction. They can't escape out in any of these directions. So they're just going to, they can only move back and forth here. That's a weak confining potential. But they don't want to get too close. So they kind of evenly space themselves in this trap. But the thing is that they can still move, right? And when one of them moves a little bit, well, if it moves this way, it'll push away this atom. If it moves this way, well, the trap will push it back. So for instance, if this one starts to oscillate here, to move over here, it'll then get pushed back, and then it'll come back and go this way. And that will push this one away. And so if you think about this, it's a chain of harmonic oscillators. And when you solve it, you get a phonon mode. Well, there's actually, in this case, there's 2 phonon modes. So there's the one where both of these things are moving together and maintaining a constant distance. And there's the breathing mode, where they go in opposite ways. So like, yeah, just like this. We're going to focus, at least for this discussion, on the first one, the case where they move together. But people have done stuff with the higher modes as well. So at least at low amounts of oscillation, we can think of this as a harmonic oscillator. And the Hamiltonian of that phonon is then h bar nu a dagger a. So nu is the frequency of the oscillation, and a and a dagger are the creation and annihilation operators for the harmonic oscillator. Right now, this phonon is totally separate from what happens to the electron. There's no coupling between them, but we're going to, of course, couple them in a minute. Otherwise, I wouldn't be bringing it up. But we can look at the energy levels of this joint system, phonon and electron. So we're going to have the ground and excited. Sorry. So this is ground with 0 phonons and excited with 0 phonons. And then we can look at the levels that have 1 phonon. So this one here is going to be ground with 1 phonon, and this is excited with 1 phonon. And ground with 2 phonons, and excited with 2 phonons. So they form this kind of ladder, or steps, if you like, 2 pairs of steps. Okay? And typically, I think the relative energy levels are roughly what I've drawn here, where so this energy difference here, or the frequency difference there, is omega, and this frequency difference here is nu, which is much smaller than omega, or the energy is much smaller than omega. Yeah.
So I understand the phonon modes being, say, suppose the collective oscillations of the 2 atoms.
Yeah.
And that's a harmonic oscillator, right?
Approximately, yeah.
And that's basically the phonon modes, but we quantize it, right? What?
Yeah. So sorry. Each separate mode, you can approximate a separate harmonic oscillator. So the mode like this is one harmonic oscillator, and this mode is a separate harmonic oscillator.
Excited, and which one is the ground then?
So the ground is the vacuum of all the harmonic oscillators.
Oh, I see. So there's no, like, they're not moving here.
Well, no, of course, because, no, I'm disagreeing with you, because it's a quantum system, so even the ground state of the harmonic oscillator has some kind of basic oscillation in it. But beyond that, they're not moving.
I guess I'm not understanding the number of degrees of freedom here.
Yeah. So the number of degrees of freedom. Each of the atoms can move in either direction. So that's why there's two normal modes. But they can move by any amount, and so that's why you have a harmonic oscillator that could have arbitrarily high energy levels in principle. Now at some point it becomes anharmonic, so that's not good anymore. And yeah, the second one becomes anharmonic much faster than the first one, and I'm not really sure too much about that. But and then of course there's also the internal degrees of freedom with the electronic state, and that's important because that's our qubit. Okay. Are there questions?
So just to confirm, the
Yeah.
E and E here, they're referring to the state of the atom? Not
They're referring to, well, it is all the state of the atom. This is the state of the electron.
sorry, the state of the electron.
Yeah, that's right.
Telling us which of the two modes.
No. So the mode that I'm writing down here is always that collective mode where they're going together. I'm just ignoring the other mode. Okay, and I'm not going to couple to it at all. It has a different frequency, and you can mostly ignore it. Okay. Yeah. Okay. So. So now suppose we shine a laser with frequency omega prime here. Well, that will let us go between these two levels, right? Or these two levels, which have the same thing. But this G doesn't go anywhere, because there's no E-1 state to go to. Right? This is the vacuum of that harmonic oscillator. So we're going to use this fact to make a selective gate. And the phonon mode is, the thing about the phonon mode is that it's the same phonon mode for both atoms. Right? What I've written here is just the energy levels for one atom. But the other atom has the same kind of picture. And the phonon state is the same for both of them because it's the same mode. But of course, the ground and excited could be different. And so what's going to happen is the phonon is going to be what's called a bus that connects between the two atoms. And the two atoms are going to be our qubits. So in particular, yeah. So in particular, we're gonna start out. So this is the Sirac-Zoller gate. By doing a pi/2 pulse on atom 1 with frequency omega. And maybe I should do this on the other board. So after step 1, so if we start out in the state E, And sorry, this is supposed to be the phonon. So we start at the first atom is in the state E, and the phonon is state 0. So that will map it to ground on 1 and 1 phonon. But if we started with the state ground on 1 and no phonons, then we still have the state ground on 1 and no phonons. OK? Is everyone fine with that? OK. And then our second step is going to use another new energy level. And we're going to do a pi pulse on atom 2 with some new frequency. Sorry, this is supposed to be frequency omega prime. Omega double prime. So, so we're going to add another energy level. E prime with energy E. Sorry, maybe I'll call this E double prime just to be a little more consistent. Energy E double prime. And omega double prime is going to be E double prime minus E over H bar minus nu. And so the point is that this thing, we can so if we have one phonon, so this is E double prime minus E. So we're going to go from the excited state here to, if we did this for a time pi over 2, we'd go from the excited state here to the E double prime 0 state over here. But if we have the ground state, we won't be able to get there. And if we have the E0 state, well, there won't be a way to take a phonon out of the mode. Okay? So we have the E double prime 0 state up here, and the only case where we see something is connecting to this E1. Did that make sense? Or should I do that again? Okay. So the point is, if we have any of these three states, nothing happens. But if we get this state, then we're coupling to this state up here. Okay? But we're not going to do it for a pi over 2 pulse because we don't really want to be in this E double prime state. We're going to do a pi pulse, which means that we go here and then we go back. And when we do that, the thing is, it's just a pi pulse. It's not a 2 pi pulse. So, I mean, it's maybe not obvious from my Rabi oscillation pictures, but if you look up above that to the actual equation, you'll see that if you do a pi pulse, you get a phase of -1. Right? And obviously, if this were in isolation, a global phase of -1 wouldn't matter. But this is a phase of -1 only for this state. These states don't get that phase. So what's happening here is that if we have the state ground on 2 and well, OK, so we have 4 possibilities here. We have ground on 2, 0 on the phonon, excited on 2, 0 on the phonon, ground on 2, 1 on the phonon, and excited on 2, and 1 on the phonon. And what do we get? Well, in this case, nothing happens. We just get the state back. In this case, nothing happens. In this case, nothing happens. But in this case, we get minus the state. OK? And then step 3 is going to be to undo step 1. And so what that does is so you see what this step did, what step 1 did, was it moved our qubit from the first atom into the phonon. Right? We started with an EG for the first atom, and we ended up with a 0, 1 for the phonon. But the first atom is always in G. And so now we're going to move it back. And this gate does a controlled Z gate, which is a 2-qubit gate. It's also universal. It's equivalent to the C0 gate. And then we just move the qubit back from the phonon into the first atom. OK? So in the tutorial, you'll study how to which is today, right? It's tomorrow. OK. You'll see how to convert this back into a C0 gate. Yeah, and you'll also have a different 2-qubit gate construction to study. So anyway, so that's our 2-qubit gate. It's universal, so that completes these DiVincenzo criteria. We have universal set of gates. We have qubits that we could, in principle, make more than one, make multiple ones. They have relatively good decoherence times, and we can initialize them and measure them. Oh, yeah, so sorry. The one thing that I left out about initialization was now we not only need to get the atoms all in the ground state, but we need to get the phonon in the 0 mode. OK? And that's a bit more challenging. But you can use the same kind of level structure and technique to do that. How do you do that? Well, so what we can do is we prepare all the atoms in the ground state, like that. And then you shine this laser with frequency omega prime. Right? And what does that do? Well, if there's a phonon mode, if we're up here or here or here, it takes out one phonon and it puts the atoms all in the excited state. And then we can do that again to move all the atoms back to the ground state. And then we repeat this process and take another phonon out of the ground state. OK? And you keep doing this for a while, and eventually you can get down to this state, and then from there to here. OK? So that's process called sideband cooling. But it is a bit more tricky to get it working right and to actually get. In order to make these Sirac-Zoller gates work well, you really have to be in the ground state of the phonon. If you're in the first excited state, they don't work at all. And so you have to be very high fidelity to the ground state. And that's challenging. And so that's one of the reasons that this Molmer-Sorensen gate is a bit more attractive that you'll study in the tutorial. OK, that's probably enough for today. So tomorrow I'll say a few words about kind of scaling up these ion traps and start talking about superconductors and hopefully a little bit about other implementations. OK, thanks.